Welcome back to Statistical Methods. This is Week 10, Lecture 2, where I will be covering the third installment of Analysis of Variance. Now, to this point, we only learned how to ask whether there are any differences at all among three group means. Now, this type of test is known as an omnibus test, with omnibus meaning comprised of several parts. Essentially, this is a test of whether our ID has an effect on our DV in the broad sense, ignoring which groups differ and by how much. So the omnibus test effectively tests this null hypothesis that all three group means are equivalent versus any other outcome. But usually researchers don't care about whether there is any difference at all in means. Rather, they usually want to know if there are specific differences between specific groups. Today we'll discuss some ways of how to go about conducting follow-up tests that answer these kinds of questions. Before we do so, however, we'll need to understand an important related concept, alpha inflation. Now, alpha inflation refers to the fact that our type 1 error rate increases as the number of hypothesis tests we conduct increases. Now, why does this occur? Recall that alpha equals the probability of rejecting the null hypothesis when that null is true. So, including that there is a difference between group means when this difference does not exactly or actually exist in the underlying populations. As discussed earlier in the course, we set our experiments alpha ourselves when we chose the significance level of 0.05. The problem, though, is that the significance level, or alpha, only stands when conducting a single hypothesis test, and this is rarely ever the case in practice. So the probability of finding a false positive statistically significant result goes up as the number of hypothesis tests goes up. Because the likelihood of finding a significant result merely due to chance increases as the number of hypothesis tests increases. So remember what a p-value of 0.05 means. You would expect to find a result as or more extreme than the one you did 5% of the time when the null is true. Thus, even when the null is true, we expect 1 of 20 tests to reach statistical significance due to chance alone, as opposed to a true effect of our independent variable. So the more tests you conduct, the more likely it is you'll happen upon one of these chance results. We can easily see this in practice. When conducting one hypothesis test, assuming the null is true, the probability of significance is 0.05, and the probability of obtaining a not significant result is 0.95. But when conducting two, assuming the null is true, the probability of two statistically significant results is 0.05 times 0.05, or 0.0025. The probability of just the first test being significant is 0.05 times 0.95, or 0.0475. The probability of just the second test being significant is the same, 0.95 times 0.05, or 0.0475. And this sums up to 0.0975. So the probability of both tests being non-significant is 0.95 times 0.95, or 0.9025. Thus, we jump from a 5% chance to a 9.75% chance of committing a type 1 error, with either one or both of our tests coming out statistically significant, just by conducting one additional hypothesis test. The number continues to rise as the number of tests increase. With 3 tests, alpha goes up to 14.3, with 4, 18.5, 5, 22.6, and with 6 tests, 26.5. Calculation here is 1 minus 0.95 to the power of the number of tests being conducted. This total probability of committing a type 1 error across all of the hypothesis tests you conduct an experiment is referred to as your family-wise error rate. Now, researchers conducting many hypothesis tests without doing something about family-wise error is one of the reasons you will sometimes see claims like this being made. Now, how does this relate to the omnibus test and its follow-ups? Usually, researchers will first conduct an omnibus test, then use this as a basis for whether or not to test differences between pairs of means. So if an omnibus F is significant, they look for significant differences between specific groups. If it is non-significant, they usually do not conduct follow-up tests. One of the primary arguments for doing things this way is that it prevents unnecessary hypothesis tests, because conducting such tests would increase type 1 error rate, or the chances of finding a false positive. So when researchers have a specific a priori, meaning before the experiment was conducted, hypothesis about differences between pairs of means and the omnibus test was statistically significant, they will often conduct follow-up tests known as planned contrasts. For example, in our adaptive memory example, the researcher probably would have hypothesized that memory in the survive condition would have been significantly better than memory in the two other conditions, the self or pleasant conditions. Thus, this researcher would conduct these two planned contrasts if the omnibus test was significant. In some cases, researchers might not have a priori hypotheses about specific group means. So instead, they may simply want to test all possible pairs of means for significant differences. These types of tests are referred to as post hoc tests. So how many pairs are possible? This can be answered with a simple formula, where k is the number of total groups or levels of the independent variable. And the formula is k times k minus 1 divided by 2. So in our last example, the adaptive memory example, we had 3 groups. So 3 times 3 minus 1, so that's 3 times 2 divided by 2. 3 times 2 is 6, divided by 2 is 3. So that's the number of comparisons we can make. Group 1 compared to group 2, group 1 compared to group 3, and group 2 compared to group 3. The problem, though, as discussed earlier, conducting many hypothesis tests will lead to alpha inflation. Because of this, post hoc tests will usually be accompanied by some method of alpha correction, lowering the significance level we test our post hoc test p-values against to avoid false positives. In other words, requiring a more extreme result in order to reject the null hypothesis. There are many kinds of post hoc tests that are defined primarily by the type of alpha correction they apply. Most of these are t-tests. You have Tukey's HSD, or honest significant difference, Fisher's least significant difference, which is ill-advised, the Bonferroni test, and the Chef's test. Now, while learning how to conduct and calculate specific post hoc test statistics is beyond the scope of this course, we can look at one method of alpha correction, the Bonferroni procedure, which is probably the most commonly used in practice. In this procedure, we divide our desired family-wise error rate by the number of tests we plan on conducting, then use this as the significance level for each individual hypothesis test. So if we plan on conducting 3 hypothesis tests, we would no longer use a cutoff of p equals 0.05 to determine whether our result is significant, but rather a cutoff of 0.05 divided by 3, or 0.017. Now we will only reject the null of one of our post hoc tests if our p-value is lower than 0.017. Another way you can do this is by multiplying your obtained p-value by 3, then comparing to 0.05. This achieves the same thing. So to summarize, when the omnibus test is statistically significant, indicating some effect of our IV on our DV, researchers will do follow-up tests comparing pairs of group means. And these are usually t-tests with an alpha correction. They could do planned contrasts if a smaller set of specific group differences were hypothesized in advance of the experiment, or they can do post hoc tests if you simply want to test all possible pairs of means against one another. Now, a question here, is it necessary to use an alpha correction even when doing planned contrasts? Most researchers don't do this in practice, but yes, you can still use something like the Bonferroni procedure to guard against type 1 error inflation, even if it's just for a small handful of planned contrasts. So straightforward answers to questions like these don't exist, and many of the issues are still being debated in the psychological literature. And you can check out this wiki page here to look at some of the important considerations that are being discussed in the field. My 2 cents is that what matters most, more than which specific test you're going to use, is that you're doing something to control the type 1 error inflation and to avoid these false positives. Assuming we're correcting alpha in some way, the omnibus test is probably unnecessary in most cases, though the omnibus effect size estimate, R squared, can still be informative, gauging how much overall variability in our dependent variable is accounted for by variability in our independent variable. That's all for this lecture. I'll see you guys next week.